So our goal in this video is to answer this question. How do you know if your model is actually good? There's a couple different tools we can use to determine if a model is good at predicting Y values. Before we get started, I'd like to apologize for my poor lighting situation. I'm not a professional YouTuber. I don't have like a ring light. I just have like a $5 Target desk lamp. And I'm recording this in July and it's really hot, and so I need to leave that shade closed, otherwise this room seriously gets to 90 degrees. But anyway, I'm not super sunburned. I just have bad lighting. All right, so we're going to do this activity that you can mostly do on your own, and then I'll just kind of show you what you've done. It's going to walk us through the 3 different tools we can use to decide if our model is good or not. Here's the premise. We have 5 students, alphabetical. We know their IQ scores, but they've been mixed up, so we don't know whose is whose. And the counselors are trying to figure out whose score goes with who. So they do have access to the students' GPAs, and one of the counselors finds this line of best fit from, I don't know, a website or maybe a statistics teacher. Yours is fixed, mine had a little typo. You take GPA, multiply it by 16, and you add 57.3, and that gets you a prediction for the student's IQ. So here are the 5 students and their GPAs. What we're going to do is we're going to use this regression line to predict their IQ scores, and then it lists their actual IQ scores, which the counselor don't have access to, but I'll give them to you. What you're going to do is calculate each residual. Remember, a residual is an observed value minus its predicted value. And then once you've done that, you're going to plot the residuals using this over here, and this x-axis is the GPA, the y-axis is the residual. So instead of plotting like GPA versus IQ, it's GPA versus residual. So I want you to do all of those before we continue. Pause the video and do everything through the plot. Okay, so we have the predicted IQs, we have the residuals. 3 of them are negative, 2 are positive. Remember, positive or negative does make a difference with residuals because it tells you if the line over or under predicted. Now for the plot, I haven't done this part yet, so we'll start with Adam. He had a 1.8 GPA, which is around here. His residual was negative 1.1. Bernard is Bernard 2.4 is his GPA, and his residual is negative 0.7. So you can see that for 2 of the students, the residuals were very large, and for 3 of the students, the residuals were pretty small. What we just made is called a residual plot. It's just a plot of the residuals. What you want to see in a residual plot is no clear pattern or random points. So what we have here, there are 2 that are pretty large, but I don't see a pattern. So this residual plot tells us that our line is actually pretty good at predicting values. I drew an example here of a bad residual plot, and you can't really see it, so let me highlight this. These points at the beginning are very close to 0, and then they get further away the larger x gets, which creates what many textbooks call this horn pattern. This residual plot should cause some alarm bells to go off, because look, this line is really good at predicting when x is small and really bad at predicting when x is large. The scatter plot might look something like this. It's actually something like exponential decay, and if we just put a line on it, the line is really good at predicting when x is small and then gets worse and worse as x gets larger. So when you're looking at a residual plot, you want to see no clear pattern, just a random cloud of points. The biggest thing to look out for is this horn pattern or any like clearly defined shape. We want random. Now we have a different counselor who does not have time to use the equation. If they didn't have time to do the calculations, what would be the best guess? So this counselor is admitting he just has to guess. He doesn't have time. The best guess would probably be the average or the mean IQ at the school, or maybe the mean IQ of those particular students. So I'll just tell you, the mean for our students is 103. So this counselor is going to predict 103 for all 5 students. Is it a great guess? No. But if he has no time, it's probably the best guess that he can make. So we'll call it the best worst guess. The next thing you're going to do is calculate the residuals. Here it's called error. You can kind of see that those are the same thing. A residual and an error, they're both telling you like how badly the line predicted, so kind of interchangeable. But once again, you're doing the actual minus the predicted, and then what I'd like you to do is square all of those and then add them up and just write them in the box. And then why don't you do the same thing for the original counselor? We already have the residuals, I filled them in for you. Square all of those residuals and then add those up. That way we can compare counselor 1 and counselor 2. So take a moment and fill out these two tables. Okay, so you can see that once we've squared them, we can actually add them up. Now, if you're a student who likes to question your teacher, you might have thought, I wonder if these residuals actually add up to 0. I don't think they do. I think they're almost 0. I did have to round a little bit for the equation, so that's why these don't quite add to 0. The question we want to answer now is which counselor did a better job of predicting IQ values? Counselor 1, who used the mean for everyone, or Counselor 2, who used the line of best fit? I think it's pretty obvious that Counselor 2 did a better job, and not just because they spent more time on the task. Now, I had you calculate the sum of the squared errors so that we would have a single number to describe how well each counselor did. Now it's true, we can look through the table and say, oh, these residuals seem smaller than these residuals, but isn't it nice to just have a single number? Counselor 2 had 89.89 for his sum of squared errors. Counselor 1 had 730, much larger. Now we're going to do two things with these numbers. The first is to calculate the percentage improvement of the sum of squared errors from Counselor 1 to Counselor 2. So to do that, we're going to start by figuring out how much better Counselor 2 was. So we're going to take the 730 and subtract 89.89. So this is how much better Counselor 2 was. And then we're going to take that and divide it by 730. This gives us a proportion. I guess I should write it as a percent because it asked for percent improvement. So this is how much better Counselor 2 was than Counselor 1. If it makes more sense to calculate this a different way, you can also do 89.89 divided by 730 and then do 1 minus that number. That works too. It's basically the same calculation. Either way you do it, what we just calculated here is called the coefficient of determination, more commonly referred to as R squared. And yes, it is related to that other R, and we will get there. All right, the next question says we could also find each counselor's typical error. Use algebra to turn the sum of the squared errors into the average error for Counselor 2. So the sum of the squared errors was 89.89. Pause the video and see if you can get to the average error for Counselor 2. So to do that, we have to start by finding the average squared error. So we're going to take 89.89 divided by 5, because there were 5 kids. So this is our average squared error. If we just want the average error, we have to square root it. Now this is called the standard deviation of the residuals. These are the other two tools we can use to decide if our model is good at predicting. We did all that work by hand. Now let's see if a calculator comes up with the same values. Now you can calculate R and R squared on your TI if you have an 83 or an 84. It's much harder to calculate S. It's a lot of clicking. So for right now, we're just going to use Statlet. So go to Statlet, select two quantitative variables, use GPA as your X and IQ as your Y. Okay, once you get there, you can see that here's the equation of the line, and you can see how I rounded it a bit, which is why our residuals didn't quite add up to 0. But R is 0.936. Here's S, 5.473. That's a little different than what we got. And R squared is 0.877, which is exactly what we got. Okay, so before we continue, I just want you to try this. Do 0.936 squared. Oh, what do you know? 0.877. So yes, R squared is literally just R squared. You don't really need any fancy technology to figure out R squared if you know what R is. You just have to have a calculator that can square a number for you. Okay, now in my other color, I'm just going to mark a couple things. You will notice that these numbers are exactly the same, which is so cool. We calculated R squared by hand, essentially. A couple things to know about R squared. It is literally just R and then squared. It's called the coefficient of determination, and it tells us how good our line is at predicting values, not just if the relationship is positive or negative or how strong the relationship is. A really common question, so common that it's pretty much guaranteed to be on an AP test, is interpret R squared. Now this is the first of many interpretations that I'm going to show you that's essentially a Mad Lib that you can fill in anytime. You don't need to reinvent the wheel with these interpretations. You can use the same setup each time. About blank percent, or R squared percent, of the variation in Y, and include context, is accounted for by the least squares regression line. You could also say explained by the least squares regression line. So in our case, we would say about 87.7% of the variation in actual IQ is explained by the least squares regression line. Now let's take a moment and see what that means, where that's coming from. This is a program called Geometers Sketchpad. I did not write the code for this particular example. It came from these teachers here and also this teacher. What we have here is 6 points. It's not quite the same scale as our GPA IQ example. These people don't have 1, 2, and 3 as their IQs, but let's just say here's GPA, here's IQ. So here's what I want to show you first. This dotted line going across your screen is the mean of Y. You'll remember in the GPA example, the counselor who didn't have time just used the mean IQ as his guess. So here's just the mean of Y, and you can see for each point, the residual is drawn, so the vertical distance from the point to the line, and then that residual is squared. And when we're squaring the residual, we are literally just making a square out of it. This square here, this square is the sum of all of the squares. So like if I make this bigger, that sum is going to get bigger. It's essentially the 703. Was it 703? 730, my bad. This is the 730. It's adding up all those squared residuals. So you can see that this line is not great at predicting. Okay, so we're going to hide that, and we're going to get the actual regression line. This is the least squares regression line. Here are the squared errors for this line, and you can already see this sum of all those errors is so much smaller than that red sum. You can see if I move it around, the line moves to minimize the squared residuals. And now let's compare. We're going to show both at once. So you can compare here the sum of the squared residuals for the regression line and the sum of the squared residuals for that mean, which we called the best worst guess. Okay, now it's showing you the area of those two squares. So we've got the area of the blue square, area of the red square, and we can do that same calculation that we did in the GPA activity. I can do 3.11 minus 1.27, 1.84. That's how much better the blue line is compared to the red line. And then if I divide that by 3.11, I get 0.59, which is R squared. Now at no point will the College Board ask you about the red squares and the blue squares, and they won't ask you to recreate this drawing, but it does illustrate where R squared comes from, and I hope that makes more sense than just memorizing how to interpret. Okay, so now let's go back and look at standard deviation of the residuals, because the one we calculated was 4.24, and the one that Staplet gave us was 5.473, which is not quite the same. They are close, but they're not exactly the same like R squared was. The reason for that is the formula actually divides by n minus 2, and we just divided by n. The reasoning for that is not really important at the moment, especially because you'll probably never have to calculate this by hand again. So we're not really going to get into the n minus 2 at the moment. The important things you have to know about standard deviation is that it's the standard deviation of the residuals, and you have to know how to interpret. So once again, this is kind of a Mad Lib sort of interpretation that you can always use. The observed values of Y context are usually about blank away from the values predicted by the LSRL, the least squares regression line. So in our case, the observed values of IQ scores are usually about 5.473 points away from the values predicted by the line. I can show you the equation for standard deviation of the residuals. It's a bit much to do by hand. It involves calculating all the squared residuals, adding them all up, dividing by n minus 2, and then taking the square root. Exactly what we did earlier in this activity, except n minus 2 instead of n. Even with 5 data points, that was a pain. So more often you'll just be given S and you'll be asked to interpret or use it. I do not have access to Minitab. I have been told it's expensive, but the College Board likes to use Minitab outputs. They are very easy to read. You'll probably see a lot of them in your textbook if you're using a textbook. But just a heads up, when you see a Minitab output like this, let me just show you around a little bit. Now clearly this is a different example because we're talking about the length of fish. I can't remember what the y variable was. It was like length of fish and it was something gross. It was maybe like number of eggs produced or something weird like that. But this is our x variable, and then this COEF stands for coefficient. The coefficient of the x variable is the slope, which makes sense if you think about y equals mx plus b. The coefficient of the x variable is the slope. And then coefficient of the constant, this is the y-intercept. So the constant doesn't really have a coefficient. There's your y-intercept. You don't really need any of this stuff, at least for now. This is the standard deviation of the residuals. This is r squared. And this is r squared adjusted, which you also don't need to worry about for right now. Now, you'll notice they don't give you r, but if you square root r squared, you will magically also have r. So that's how Minitab outputs work. You might see some in your book or in some College Board questions. Okay, so let's summarize. Let's go back to the original question. How do you know if your model is a good model? Here are the 3 different tools you can use to evaluate your model. You can use residual plots. Remember that you want to look for no clear pattern. If you see a scattering, a cloud of points with no clear pattern, you're good to go. You can use the standard deviation of the residuals to tell you the typical size of the residual. You want the residuals to be fairly small, so a large standard deviation of the residuals is probably not that good. And you can use the coefficient of determination, which is r squared. Once again, that tells us what percent of the y variation is explained by the regression line. You want r squared to be large. You want to be able to say, look at my line. 90% of the variation in y is explained by the line. It is so good at predicting y values. So you want S to be small, you want r squared to be large, you want the residual plot to show no clear pattern. Now let's not forget about our old friend, the correlation coefficient, or R. R told us the direction and the strength of a relationship. So if it was positive or negative, and if it was strong, weak, moderately strong, or not strong at all. It didn't tell us if the line was good or not. And remember that you do need to see a scatter plot. You can't just look at R and say, it's a strong linear relationship. Because as we saw in a previous video, you can have a clear parabola and have an R value of like 0.7. This is an example where the residual plot for this would be some good evidence that this line is probably not good at predicting values. So don't forget about R, it is important. It just doesn't tell you if the line is good at predicting. If you're asked, is this line good at predicting y values, these are the tools you want to use. If you're asked to describe a scatter plot, R can be helpful. Now I know statistics can be kind of frustrating compared to other math classes because we're not just finding x equals something and circling it. There's a lot of explanation involved. And on a question like this, is this line a good predictor of y? It's really important that you explain why you said yes or no and use some of these tools to back up your answer. It's very similar to an English essay where you make a claim and then you have to bring in evidence from the reading that support your claim. If you make a claim that a line is a good predictor of y, bring in some evidence and show why you're saying that. All of the tools we learned about in this video are ways for you to bring in some evidence to back up the claims that you're making.